Welcome to Thought Frontier.
Welcome back for another deep dive. You guys have sent in some pretty heavy stuff this time around.
Yeah.
We're talking about thermodynamics and information and how complex systems develop. Okay, so mission today. Distill these dense concepts into some understandable takeaways.
Okay.
We're going to explore why things grow, why they decline, and what this means for us humans and our impact on the planet.
It all begins with, probably a concept that everyone's heard of, the second law of thermodynamics.
Okay.
But it's more than just a scientific principle. It's
Yeah.
kind of a story about energy's journey.
The universe constantly striving for balance.
Right.
Like it's still trying to smooth out all the wrinkles from the Big Bang.
Precisely. That smoothing out process is what we call entropy production.
Okay.
You can think of it as the universe's kind of tendency to just spread energy out as much as possible, always flowing from high concentration to low concentration.
Okay.
That's the essence of the second law.
So things are always becoming more disordered. I guess that's not a very hopeful picture.
Well, hold on, because this is where things get really interesting.
Okay.
Even though the universe has this kind of drive toward disorder, these pockets of order and complexity, they pop up everywhere.
Yeah.
And that's where we get to these things called dissipative structures.
Dissipative structures. Okay, you're losing me already. Help me out here.
Think of it this way. Dissipative structures are like expert energy managers.
Okay.
They form as a way to tap into the natural flow of energy and accelerate that dissipative process.
Okay.
And get this, they're all around us. Tornadoes are dissipative structures. Ecosystems are dissipative structures. Even human societies can be considered dissipative structures.
Wow. So they're like entropy-producing machines, but in a way that creates order and complexity. My mind is bent.
It is. And here's the kicker.
Okay.
As they grow, dissipative structures become even more complex, increasing their ability to dissipate energy gradients.
Okay.
It's like this positive feedback loop where complexity feeds on itself.
But if they're so good at this energy management thing, why don't they just keep growing forever? I mean, there's got to be a limit, right?
You're right, there is a limit,
Yeah.
and that's where the Minot-Aoki law comes in.
The Minot-Aoki law.
This law describes a pattern that we see across a surprising range of systems,
Right.
from organisms to ecosystems to even economic cycles.
Interesting.
It basically tells us that all dissipative structures, no matter how efficient,
Yeah.
eventually they hit a ceiling.
So everything that grows eventually declines.
Yeah.
Like this sort of rise and fall to it all.
Exactly. And one of the proposed explanations for this decline by the scientist Stanley Salthe is this idea of information overload.
Information overload.
Picture this. You're trying to cram more and more information into a room, but the room's not getting any bigger.
Yeah.
Eventually, it becomes too much, things get cluttered, and it's harder to find what you need.
Okay, I can definitely see that happening in my office.
Right.
But how does that apply to like an ecosystem?
Think about it in terms of a system's ability to process information.
Okay.
If an ecosystem becomes overloaded with information, its ability to adapt and respond to change just slows down. It becomes less efficient at managing energy flow, and eventually it starts to decline.
This is making me think about human impact on the environment. We're constantly simplifying ecosystems, right?
Yes.
Cutting down diverse forests, replacing them with single crop fields, things like that.
You've hit a critical point. When we simplify ecosystems like that, we're actually reducing their maturity in terms of energy flow and information processing.
Oh.
We eliminate species, we homogenize landscapes, we impose artificial structures that constrain those natural processes.
So we're kind of forcing these ecosystems back to a simpler, less mature state.
Precise.
And that's messing with their ability to manage energy efficiently.
Precisely. And while that simplification might give us temporary access to energy flows, think about our reliance on fossil fuels.
Yeah.
It often leads to unintended consequences, things like pollution, waste, and a reduction in the system's overall resilience.
It's like we're getting this sort of short-term energy boost at the cost of long-term stability.
That's a great way to put it.
Okay.
And this isn't just limited to ecosystems.
Right.
Human societies themselves, we exhibit this pattern of growth, complexity, and eventual decline.
So if I'm understanding you correctly, this Minot-Aoki law could potentially apply to everything, from a single cell to an entire civilization.
That's the fascinating implication of this law.
Wow.
It suggests this kind of universal pattern in the way that complex systems develop and evolve.
Okay.
And it raises some pretty profound questions about the long-term sustainability of human civilization.
This is really making me think about our place in the grand scheme of things.
Right.
If we're just another dissipative structure subject to these same laws of energy and information, where do we go from here?
That's where this emerging field of infodynamics comes in.
Infodynamics.
Infodynamics seeks to understand how information interacts with the physical world,
Okay.
shaping the development and evolution of those complex systems.
Okay. So infodynamics is all about the interplay between information and energy.
Yes.
But how do we even measure something as abstract as information?
That's the challenge.
Yeah.
There's no single ruler for measuring information, especially when we're dealing with these complex systems. But researchers are coming up with these new ways to try to quantify different types of information and understand their interactions.
Okay, so what kind of insights are they uncovering?
Well, for example, they've identified these different types of information, each with its own role to play.
Okay.
You know, structural information, entangled information, synergic information, noise.
Okay, hold on. You lost me back there at entangled information.
Right.
Give me the SparkNotes version of what those all are.
Okay, let's start with structural information.
Okay.
Think about the arrangement of atoms in a molecule, the connections in a neural network, the organization of a city.
Okay.
The specific way things are arranged that carries information that influences how the system functions.
So it's not just about the individual parts,
Right.
but how they're connected to each other.
Exactly. The way information is encoded in the structure of a system is crucial for understanding how it operates.
Okay.
And it's not limited to just physical structures either. We can talk about the structure of information itself, like the syntax of a language
Right.
or the logic of a mathematical equation.
That's really interesting.
Right. It makes you realize how much we take information for granted.
Yeah.
But what about this entangled information?
Yeah, that sounds like something out of Star Trek.
It might sound like science fiction,
Yeah.
but bear with me.
Okay.
Entangled information is a concept from quantum physics.
Oh, quantum physics.
And it refers to the way that two or more particles can become linked,
Okay.
even if they're separated by these vast distances.
So they're sharing information instantaneously, faster than the speed of light.
That's what makes entanglement so mind-boggling.
Yeah.
It challenges our classical understanding of causality and space-time.
Right.
The key takeaway for infodynamics is that entangled particles have a shared history,
Okay.
and that history is encoded in their entangled states.
Okay, so entangled information is about the shared history of a system, whereas structural information is about the current arrangement of its parts.
Exactly.
Look, what about this synergic information? Does that have something to do with synergy?
You got it. Synergic information refers to the information that emerges when different parts of a system interact and work together.
Can you give me an example?
Yeah, imagine a team of scientists collaborating on a really difficult problem.
Right.
Each scientist brings their own knowledge and expertise to the table,
Mm-hmm.
but it's their interaction, their sharing of ideas and perspectives that leads to those new insights and breakthroughs.
Okay.
The synergy of their combined efforts generates this new information that wouldn't exist otherwise.
It's greater than the sum of its parts.
Exactly. And it's this key driver of complexity and systems of all kinds, from biological ecosystems to human societies.
So synergic information is about the creative potential that comes from that collaboration and exchange of ideas.
Precisely.
Interesting.
And then finally, we have this noise. And it's a common misconception that noise is just like random, useless information. While noise can be disruptive, it can also be a source of novelty and innovation.
Really?
Think about genetic mutations.
Okay.
Basically, they're random changes in the genetic code, a form of noise.
Right.
But sometimes those random changes can lead to these beneficial adaptations that drive the evolution of new species.
So noise can actually be a catalyst for change and evolution.
It can.
Huh. That's a really fascinating way to look at it.
Right. And it kind of challenges our assumptions about what's useful and what's not.
Yeah, it really does.
But you know, this is all getting pretty abstract.
It is? Yeah.
How do we connect these different types of information to real-world phenomena?
Yeah, how does this all play out in the way that things actually grow and develop?
That's a great question, and it leads us to one of the most intriguing discoveries in infodynamics. The second law of infodynamics.
Hold on a second. Another law.
Another law.
Is this going to blow my mind as much as the second law of thermodynamics did?
It just might.
Okay.
This second law was proposed by a researcher named Melvin Vopson.
Okay.
And it states that, unlike entropy, which tends to increase information, entropy actually tends to decrease over time.
Wait, are you saying that information is getting more ordered?
Yeah.
How is that even possible? I thought the universe was all about increasing disorder.
It's a bold claim, but Vopson has found evidence for this law
Really?
in a variety of systems,
Right.
from the way digital data degrades to the patterns of genetic mutations, and even in the way electrons arrange themselves within atoms.
So he's suggesting that information is being selectively preserved
Yes.
and refined over time,
Yes.
even at the most fundamental levels of reality.
It seems so.
Wow, this is starting to feel like we're uncovering some hidden order within the apparent chaos of the universe.
Exactly.
But before we go any further down this rabbit hole, I
Yeah.
think we need to take a step back and unpack this whole information entropy thing.
Well, the best place to start is to contrast it with thermodynamic entropy,
Okay.
the concept we were talking about earlier.
With the second law of thermodynamics.
Precisely.
Okay, so thermodynamic entropy is all about that tendency for energy to disperse.
Yes.
And for systems to become more disordered over time, right?
Exactly.
It's a measure of how spread out energy is within a system.
Yes.
The higher the entropy, the more disordered the system.
Right. Think about a hot cup of coffee cooling down.
Okay.
That heat energy is spreading out into the surrounding environment,
Yeah.
increasing the overall entropy.
Okay, that makes sense.
Right.
But how does information entropy fit into this?
Well, information entropy is a bit different.
Okay.
It's a measure of how much uncertainty or unpredictability there is in a system. The higher the information entropy, the more random and unpredictable the system is.
So high information entropy equals lots of randomness. Low information entropy equals more order and predictability.
You got it. Think about a coin toss
Okay.
that has high information entropy because the outcome is unpredictable.
Right.
But if you had a coin that always landed on heads,
Okay.
that would have very low information entropy because the outcome is certain.
Right.
So you can see how they're kind of measuring different aspects of a system.
Okay, I'm starting to wrap my head around this.
Yeah.
So how does Vopson's second law of infodynamics fit into all of this?
Right.
If information entropy tends to decrease, wouldn't that mean that everything in the universe should be becoming more ordered
Right.
and predictable?
Mm-hmm.
And wouldn't that kind of contradict the second law of thermodynamics?
That's a great question. And that's where things get really interesting.
Okay.
And we'll pick up in the next part of our deep dive.
Okay.
The second law of infodynamics doesn't negate the second law of thermodynamics.
Mm-hmm.
Instead, it suggests that there's this counterbalancing force at work,
Okay.
a drive towards information order. Right.
That exists alongside that drive towards energy disorder.
This is blowing my mind. It's like there's this hidden dance between order and disorder,
Yeah,
information and energy,
it is.
playing out at every level of the universe.
At every level.
I can't wait to explore this further in the next part of our deep dive.
I'm excited to dive in.
Me too. So last time, we were talking about this idea of information entropy and how it seems to be decreasing over time, according to the second law of infodynamics.
Right.
But I think you were about to explain how this idea of decreasing information entropy actually fits with the second law of thermodynamics, which tells us that entropy overall is always increasing.
Right.
How can those two things coexist?
That is the million-dollar question, isn't it? It's like we have these two seemingly opposing forces at play in the universe.
Yeah.
This drive towards disorder in the realm of energy.
Right.
And this drive towards order in the realm of information.
It's making my head spin, but it's also super exciting.
It is. It's like we're discovering this whole new layer of complexity in the universe.
Exactly. And I think it's important to remember that the second law of infodynamics doesn't contradict the second law of thermodynamics.
Okay.
They're not like fighting each other.
Right.
Instead, they seem to be operating in tandem,
Okay.
like two sides of the same cosmic coin.
Okay, that makes sense.
Yeah.
So as the universe is expanding and becoming more disordered from an energy perspective,
Right.
it's simultaneously becoming more ordered from an information perspective.
That's a great way to visualize it.
It's like a cosmic balancing act.
It is. And this brings us back to the research of Melvin Vopson, who, proposed this second law of infodynamics.
Right, right.
He's done some really fascinating experiments to test this idea.
You mentioned that he looked at everything from digital data to genetic mutations.
Yes.
Can you give me some specific examples of how he actually tested the second law?
Absolutely. One of his earliest experiments involved looking at digital data storage.
Okay.
He used a technique called micromagnetic modeling
Okay.
to simulate how magnetic data degrades over time.
Okay.
Basically simulating how data gets corrupted.
Right, okay.
And what he found was fascinating.
What did he find?
As the data degraded, the information entropy actually decreased.
Wait, so even as the data was becoming more corrupted and seemingly random,
Yeah.
it actually became more ordered from an information perspective?
Yes, and it might seem counterintuitive.
Yeah.
But remember what we said about information entropy?
Yeah.
It's a measure of unpredictability.
Okay.
As the magnetic bits in the simulation flipped randomly, they tended towards a state of equilibrium where each bit had an equal chance of being a 0 or a 1.
Okay.
So even though the data was becoming more random in a physical sense,
Right.
it was becoming more predictable in a statistical sense. And that increase in predictability corresponds to a decrease in information entropy.
Okay, that's starting to make sense.
Good.
But what about biological systems?
Right.
You mentioned that he also looked at genetic mutations.
Yes.
How do those fit into the picture?
So this is where things get even more interesting.
Okay.
Vopson analyzed RNA sequences from the SARS-CoV-2 virus.
Okay.
You know, the virus that causes COVID-19.
Right.
And he tracked how those sequences mutated over time.
Okay.
He looked at two types of mutations: deletions, where nucleotides are removed from the sequence, and single nucleotide polymorphisms, or SNPs, where one nucleotide is swapped for another.
So he was basically looking at the typos that happen when genetic information gets copied.
Exactly.
Okay.
And what he found was that both types of mutations tended to result in a decrease in the information entropy of that RNA sequence.
So even these seemingly random genetic errors
Yes.
are actually pushing the system towards greater information order.
That's the implication.
Wow.
And it's a pretty profound one.
Yeah.
It suggests that even at the molecular level, there might be this force driving biological systems towards greater information efficiency.
This is really making me rethink everything I thought I knew about evolution.
Right.
It's not just about these random mutations in natural selection.
Yeah.
There's this whole layer of information dynamics at play that we're only just beginning to understand.
It's a whole new perspective
It is.
on this, very fundamental process.
Well, hold on. If information entropy is always decreasing, wouldn't that mean that eventually everything in the universe would become perfectly ordered and predictable?
Right.
Wouldn't it kind of contradict the second law of thermodynamics?
That's a great question, and it gets to the heart of the interplay between these two fundamental laws.
Okay.
The second law of infodynamics doesn't mean that thermodynamic entropy will suddenly stop increasing.
Okay.
Remember, those two types of entropy are measuring different things.
Right. Thermodynamic entropy is about energy dispersal, while information entropy is about predictability.
Exactly.
But how can they both be operating at the same time? It seems like they'd be working against each other.
Think of it this way. Thermodynamic entropy is like the background noise of the universe,
Okay.
always increasing as energy spreads out and systems become more disordered. But within that sea of increasing disorder, these pockets of information order can emerge and evolve.
So it's like the universe is getting messier overall, but within that mess, things are also becoming more organized and predictable in certain ways.
Exactly. It's like this dance between order and disorder.
Okay.
Where both forces are constantly shaping and influencing each other.
Right.
And that brings us back to those different types of information we were talking about earlier.
Yes.
Structural information, entangled information, synergic information, and noise.
Okay. Yeah, we were getting into those
Yes.
before we kind of went down this information entropy rabbit hole.
Right.
I'm ready to circle back to those now. I'm really curious to hear how these different types of information play a role in this cosmic dance of order and disorder.
They play a crucial role. Each type of information contributes to the overall information dynamics of a system,
Okay.
influencing how it develops, adapts, and evolves.
Let's start with structural information again. We talk about how it's encoded in the way things are arranged,
Right.
like the atoms in a molecule or the connections in a neural network. But how does that play into this bigger picture of information dynamics?
Think about the structure of a tree.
Okay.
Its branches are arranged in a specific way to maximize sunlight exposure for photosynthesis.
Right.
That arrangement, that structure, is encoding information about how to efficiently capture energy.
So the tree's structure is literally carrying information about how to survive and thrive in its environment.
Exactly. And that's just one example.
Okay.
The structure of a protein determines its function. The architecture of a city influences its traffic flow. The layout of a circuit board dictates how electronic signals are processed.
Okay.
Everywhere you look, structure is encoding information that influences how things work.
That's incredible. It's like information is woven into the very fabric of reality.
It is.
Okay, but what about entangled information?
Right.
That one still feels a bit mysterious to me.
It's definitely one of the most mind-bending concepts in physics.
Yeah.
But for our purposes, the key takeaway is that entangled information is about shared history.
Okay, remind me again how that works.
Sure. So imagine two particles that were once connected, but then become separated. Even though they're no longer physically linked, they still share this kind of invisible connection.
Okay.
If you measure the state of one particle, you instantly know the state of the other, no matter how far apart they are.
So it's like they have this spooky, instantaneous communication channel.
That's the strange thing about entanglement.
Yeah.
It seems to defy our classical understanding of cause and effect of space and time.
Yeah.
But the important point for infodynamics is that entangled particles have a shared history, and that history is encoded in their entangled states.
So it's like their past is still influencing their present, even though they're no longer physically connected? That's so wild.
Yeah.
But how does this type of information play a role in the larger scheme of things?
It's still an area of active research.
Okay.
But some scientists believe that entangled information might play a role in everything.
Really?
From the emergence of consciousness to the workings of the universe itself.
Okay, now we're really getting into some mind-blowing territory.
Right.
But let's move on to synergic information.
Okay.
We talked about how it emerges from the interaction of different parts of a system. Can you give me some more examples of how that works in the real world?
Sure. Imagine a flock of birds flying in formation.
Okay.
Each bird is responding to its neighbors, adjusting its flight path based on the movements of the others. This collective behavior, the synergy, allows the flock to move as a cohesive unit, navigate obstacles, and even evade predators.
So it's like the information is flowing between the birds.
Yes.
Creating this kind of collective intelligence.
Exactly. And we see this same principle at play in all sorts of complex systems.
Okay.
Think about the neurons in your brain.
Okay.
Each one firing and connecting with others to process information and generate thoughts.
Yeah.
Or the cells in your body.
Right.
Working together to maintain your health and keep you alive.
Wow.
Synergy is everywhere.
This is making me realize just how interconnected everything really is.
Yeah.
It's like information is the glue that holds the universe together, allowing this complexity to emerge from the interaction of countless individual parts.
That's a beautiful way to put it.
Okay.
And it brings us to that final type of information we need to discuss.
Right.
Noise.
Noise?
We talked about how it can be a source of novelty and innovation, but I'm sure you're still a bit fuzzy on how that works.
A little bit, yeah.
Can you give me some more examples of how noise can actually be a positive force?
Sure.
Think about the evolution of music.
Right.
New genres often emerge when musicians experiment with different sounds, rhythms, and instruments.
Right.
Introducing elements of randomness and noise into that creative process.
So jazz emerged from the blending of different musical traditions.
Yes.
Rock and roll from the injection of blues and country influences. Electronic music from the exploration of these new technologies.
Exactly. It's like the noise is shaking things up and creating new possibilities.
Oh, right.
And we see the same principle in the natural world.
Okay.
Random genetic mutations, which are a form of noise, and sometimes lead to these beneficial adaptations that allow organisms to better survive and reproduce.
Okay.
Without noise, everything would become stagnant and predictable, and there'd be no room for change or evolution.
This is really making me rethink the way I view randomness and unpredictability. It's not just chaos.
Right.
It's this source of creativity and innovation.
Exactly.
A driving force in the evolution of the universe itself.
That's a great way to put it.
But I'm wondering, how do scientists actually measure these different types of information?
Right.
It seems like it would be incredibly difficult to quantify something as abstract as information.
Yes.
Especially in these complex systems.
You're absolutely right. It is a major challenge. There's no kind of one-size-fits-all approach to measuring information.
Right.
Especially when we're dealing with systems as complex as ecosystems or societies.
Yeah.
But researchers are developing new tools and techniques to try to get a handle on these different types of information and understand how they interact.
Can you give me some examples of the tools they're using?
Sure. One approach is to use network theory.
Okay.
To analyze the connections between different components of a system. By mapping mapping out that network of interactions, you can start to quantify the flow of information and identify key hubs or bottlenecks.
So it's like creating a map of the information highways within a system.
Exactly. And that map can reveal a lot about the system's dynamics and how information shapes its behavior.
Right.
Another approach is to use information theory, which was originally developed for communication systems, to analyze the complexity and predictability of different types of data.
So they're borrowing tools from different fields to try to crack the code of information dynamics.
Exactly.
That's really clever.
It is. It's a truly interdisciplinary field, drawing on insights from physics, computer science, biology, even philosophy.
It's really fascinating. But I'm wondering, what are the practical implications of all this?
Right.
How can we use these insights from infodynamics to better understand our world? And maybe even solve some of the problems we're facing?
That's the big question, isn't it? Infodynamics is still a relatively young field. And we're just beginning to scratch the surface of its potential applications. But the implications are vast. And I believe they touch on every aspect of human knowledge and endeavor.
Can you give me some specific examples of how these insights might be applied?
Sure. Let's start with ecology. If we can better understand how information shapes the development and resilience of ecosystems, we can develop more effective conservation strategies, design more sustainable agricultural practices, and perhaps even mitigate the impacts of climate change.
So we could use infodynamics to help heal the planet.
It's certainly a possibility.
Wow.
And it goes beyond just ecology. In medicine, infodynamics could lead to new diagnostic tools, personalized therapies, and a deeper understanding of how our bodies process information to maintain health.
That's really cool.
In computer science, it could inspire new algorithms, more efficient data storage, and even advancements in artificial intelligence.
So we're talking about potentially revolutionizing entire fields of study.
Yes, it's a really exciting time.
This is incredible, but it still feels like infodynamics is a very abstract and theoretical field.
It is.
How do we bridge that gap between these abstract concepts and the real world?
That's a great question, and it's something that researchers are actively working on.
What are they doing?
Well, one key area of focus is developing better ways to quantify and measure information in real-world systems.
So it's about coming up with concrete ways to measure things like structural information, entangled information, and synergic information in actual ecosystems, organisms, and societies.
Exactly. Another important area of research is exploring how these different types of information interact with each other and with the physical world.
It seems like that's where things get really complex.
It is.
How do you even begin to untangle all those interactions?
It's definitely a challenge. But researchers are using a variety of approaches, including computer simulations, mathematical modeling, and experimental studies to try to gain a better understanding of these complex dynamics.
This is all so exciting. It feels like we're on the cusp of a major scientific breakthrough.
It does, doesn't it?
But I have to admit, I'm still a little bit overwhelmed by all this.
Yeah.
It's a lot to process.
It is a lot to take in. But I think the most important takeaway is this. We are living in an information-rich universe. And the more we learn about the nature of information, the more we uncover about the nature of reality itself.
That's a beautiful way to put it. So where do we go from here? How can our listeners learn more about infodynamics and explore these ideas further?
There are some great resources available online, including articles, videos, and even online courses.
Awesome.
I would recommend starting with the sources you shared with us for this deep dive. They provide a solid foundation for understanding the core concepts. And of course, there's always more research being published all the time. So it's an exciting field to stay up to date on.
It really is. We'll be sure to include links to some of those resources in the show notes.
Awesome.
Is there anything else you'd like to add before we wrap up this part of the discussion?
Just one final thought. As we delve deeper into these mysteries of information, we inevitably encounter some of the biggest questions about the nature of reality, consciousness, and the meaning of existence itself.
Wow.
It's a journey that's both exhilarating and humbling.
I can imagine.
And I encourage everyone to join in the exploration.
That's a perfect sentiment to leave our listeners with.
Yeah.
So keep those minds open, stay curious,
Yes.
and never stop exploring the incredible power of information.
Couldn't have said it better myself.
But we're not quite done yet. We still need to dive into some of the really mind-boggling implications of infodynamics.
Yes.
Like the simulated universe hypothesis.
Right.
And we'll do that in the final part of our deep dive. Okay, so we've covered a ton of ground already in our deep dive into infodynamics. But we've been teasing this whole simulated universe hypothesis.
Right.
I'm dying to hear more about this.
Okay.
It sounds kind of like, the Matrix or something.
It definitely has that science fiction feel to it.
Yeah, it does.
But this idea that our universe might actually be a simulation is something that some physicists are actually taking quite seriously these days.
Really? Okay, so walk me through this.
Okay.
What's the connection between infodynamics and the idea that we're all living in a simulation?
Well, it goes back to this growing realization that information might not just be a byproduct of physical processes, but a fundamental ingredient in the fabric of reality.
So instead of information emerging from the physical world, it's the other way around.
Right.
The physical world is emerging from information.
That's the radical idea that some physicists are exploring.
Wow.
And if that's the case, then it's not a huge leap to consider the possibility that our universe could actually be a highly advanced simulation running on some incredibly powerful computer system.
Trying to keep an open mind here.
Yeah.
But that's a big pill to swallow.
It is.
What kind of evidence is there to support this idea?
Well, there's no direct evidence, of course.
Okay.
We can't just peek behind the curtain and see the code running our simulated world.
Yeah.
But there are some intriguing hints that some physicists point to.
Like what? Give me some examples.
Okay, so one example is the fact that our universe seems to be governed by a set of very specific laws and constants. Like the speed of light.
Right, the laws of physics.
Exactly, the laws of physics.
But why would that suggest a simulation?
Well, think about it this way. If you were designing a computer simulation of a universe, you would need to program in a set of rules to govern how things work.
Right, to make it run.
Exactly.
Yeah.
Those rules would determine how particles interact, how gravity behaves, how fast information can travel.
So you're saying that the laws of physics could be seen as like the programming language of our simulated universe?
That's one way to think about it.
Wow.
Another piece of the puzzle comes from quantum mechanics.
Okay.
Which, as you know, is full of strange and counterintuitive phenomena.
Quantum mechanics always makes my head spin.
I know, it's mind-boggling.
But how does that tie into the simulation hypothesis?
Well, one of the key principles of quantum mechanics is that particles can exist in multiple states simultaneously until they are observed.
Right, the whole observer effect thing.
Exactly. It's like they're not fully real until we measure them.
Yeah, it's so bizarre.
It is bizarre. But some physicists have suggested that this quantum weirdness could be a clue that our reality isn't as solid and continuous as we perceive it to be.
So maybe we're not actually living in a physical universe.
Right.
But a universe made of information?
Yes.
Where things only become real when they are observed or measured?
It's a mind-bending concept.
It really is.
But it's one that some physicists are exploring.
Wow.
And if our universe is fundamentally made of information, then it's not such a huge leap to imagine that it could be running on some kind of computational substrate.
Okay. I'm starting to see how the pieces fit together here.
Good.
But let's go back to Melvin Vopson and his second law of infodynamics.
Right.
How does that fit into this simulated universe idea?
So Vopson has actually linked his second law of infodynamics to the simulation hypothesis in a couple of interesting ways.
Okay.
First, he argues that the fact that information entropy seems to be decreasing over time is consistent with the idea that our universe is being optimized by some kind of external intelligence.
So like a programmer constantly refining the code of our simulated universe.
Exactly, to make it more efficient, more elegant.
Wow.
Vopson also points to the fact that his second law of infodynamics seems to apply at every level of reality, from the quantum realm to the cosmic scale.
Right, right.
He argues that this universality is further evidence that information might be the fundamental building block of our universe.
I'm getting chills. This is all so wild.
It is pretty mind-blowing.
And fascinating. But if our universe is a simulation, Then who created it?
Right.
And what's the purpose?
Those are the big questions, aren't they?
They are.
And unfortunately, those are questions that science can't answer.
Right.
At least not yet.
So we're basically left with a giant cosmic mystery.
In a way, yes.
Okay.
But that's what makes this whole exploration so exciting. You know, we're pushing the boundaries of our understanding of reality, asking questions that we never even thought we could ask before.
This has been an absolutely incredible journey. I feel like my brain is about to explode.
I know, right? It's a lot to take in.
Yeah, we've explored the laws of thermodynamics and infodynamics.
Yes.
Uncover this hidden role of information.
Yeah.
In shaping everything from atoms to ecosystems. And even ventured into this mind-blowing realm of the simulated universe.
It's been quite a ride.
It really has.
But I think the most important takeaway from all of this is that we are living in an information-rich universe.
Yeah.
And the more we learn about the nature of information, the more we uncover about the nature of reality itself.
That's a beautiful way to put it.
So to all of you listening out there, keep those minds open, stay curious, and never stop exploring the incredible power of information.
Who knows what other mysteries we might uncover along the way, right?
Exactly, and who knows, maybe one day we'll even find out if we're all just characters in some grand cosmic simulation.
Now that would be a plot twist. Thanks for joining us on this incredible deep dive into the world of infodynamics.
It was my pleasure.
Until next time, keep exploring.